We present a display technology and associated interaction techniques with the goal of producing a convincing illusion of physical realism. Our 8-dimensional, or 8D, display prototype is a general-purpose light transducer capable of simultaneously emitting a 4D light field and capturing a 4D light field. Our 8D display presents the user with a glasses-free 3D image while reacting to incident, environmental, and user-controlled light sources. In this shot, a user moves a lamp, which lights a virtual troll model. The captured and displayed light fields are spatially multiplexed through a 2D lens array on the surface of the 8D display. Because the 8D display captures the entire incident lighting function within a 19-degree cone above the display, the relit model naturally captures the properties of the lighting source. Note the difference between the previous lamp and this small flashlight. We demonstrate capturing shadows of real objects on renderings. The user's hand casts a virtual shadow on the rendered troll figure. The shadow follows the depth contours, appears sharper when cast nearer the object, and softer when cast nearer the light source, as one would expect of a true shadow. Our real-time GPU pipeline enables our 8D display to dynamically relight moving and animated models. The pipeline deinterlaces images captured from the back of the lens sheet to synthesize a 5x5 input light field, and then synthesizes a 5x5 output light field by projecting every view of the input light field onto a 3D scene and capturing the output from each output view direction. Finally, the output light field is re-interlaced for display through the lens array. Here, the interlaced views are visible. Now we show a single view of the output light field under changing input lighting conditions. In order to demonstrate that our 8D display provides a glasses-free 3D effect, we translate the camera over the display, keeping the center of the camera aimed at the center of the screen. Note how the parts of the troll that stick out, such as the feet, appear to change perspective as the camera is moved. Our 8D display provides full horizontal and vertical parallax. Interaction with an 8D display is not limited to realistic lighting. In this demonstration, we turn a normal lamp into a virtual X-ray source. We segment an MRI scan of one of the authors into a head and a brain model. The incident lighting intensity sets the transparency of the outer model, revealing the brain model when the lamp is brought close to the screen. We again show the interlaced views, this time for the X-ray demo. This is a single view from the X-ray demo under varying lighting conditions. We prototype the 8D display with a projector camera system, as sensor and pixel LCDs are not yet available at the required pitch. A 2D lens array sits in front of a projector and a camera, co-located on the screen through a beam splitter and a front surface mirror. A polarizer is used to prevent crosstalk between the polarized LCD projector and the camera. Here you can see the raw view of the lamp captured by the 8D display on the monitor to the left. To determine the center location of each lens in the lens sheet in the view of the camera, we place a collimating lens above the display. The resulting captured image is processed in MATLAB. A grid of second-degree polylines are fit to the central spots. To calibrate the projector, we generate a repeating pattern in the projected image, which will be magnified by the Moiré magnifier effect. When the pattern scale and period match those of the lens sheet, the image will appear solid red. The 8D display presents a vision for future bidirectional light-based interaction using today's emerging display technologies. We hope to demonstrate the rich potential for diverse interaction techniques that make novel use of light transport.